In this recording, we're going to learn about independence. So this can be a little bit challenging, so you're really going to have to focus here, pause the recording, possibly replay as necessary. Okay, so two events are independent when the occurrence of one has no effect on the probability of the other event happening. Okay, you might think about things like whether I wear sneakers or not and whether it rains. Okay, they each have their own probability, but my wearing sneakers has no effect on whether it rains or not. Okay? Whereas if the occurrence of one event affects the probability of the other event happening, the two events are not independent. You might think about the temperature outside and the probability of a randomly chosen student wearing shorts. Okay, so one may affect the other. Two events, formally, are defined to be independent if the probability of A, given that B occurred, is the same as probability of A. Now you might be your eyes might be glazing over when you see this notation. I get it. But think about this. What this is saying is is defined as the probability of being left-handed, and B is defined as the probability of being a male. Okay? He would say something like this. Is the probability of being left-handed, given that a person is a male, the same as the probability of any given person being left-handed? And I think you would agree that probably the same if we have a large sample. We're looking at the whole population. Well, let's flip it around. Is the probability of being male, given that the chosen person is left-handed, the same as the probability in general of being a male? Yeah, I would suppose that about 50% of the lefties are male. And flipping around here, if the probability of being a left-handed person is whatever it is, let's say it's 30%, well then I would expect about 30% of the males to also be left-handed. Let's look at a couple examples. Okay, I want you to choose here whether it is an independent or not independent event. Notice how we don't say dependent, just independent or not independent. Play the recording when you're ready. Okay, so hopefully you picked up on the fact that if I do not replace it, it's going to change the probability of getting a red marble. So these are not independent. In the second one, flip a coin, and then I'm going to roll a die. Well, those don't have any connection at all. It is completely independent, that second event. It does not depend on the outcome at all of the first event. Okay, in our spinner, let's have you find out the probability of an even, the probability of an even given that it was a prime, and the probability of an even given the outcome was less than 5. Find out A, B, and C, please. Play the recording when you're ready. So hopefully you paused and worked those out. Probability of getting even is, of course, 1/2. Probability of giving an even, given that it was a prime. So here are primes 2, 3, 5, and 7. So we only have 1, so that would be 1 out of 4. Probability of getting an even, given that the number was less than 5. So I'd be considering 1, 2, 3, and 4. And you've got 2 out of 4, or 1/2. So which events are independent? So the probability of getting an even, given that we're choosing a number less than 5, is the same as the probability of getting just an even. So parts A and C are independent. Let's get into some more challenging questions. Okay, in example 3, we're looking at 6th graders, and we're comparing male and female's choices for favorite subject. Are gender and math independent? Well, there's lots of different ways we can go here. I'm going to choose male, because it's the top one. We're going to look at what's the probability of being a male. So find out what that is in general. And hopefully you realize, okay, all the males are 30 out of 57. Might help us to put this into decimal form for comparison of different denominators. So we'll just say approximately 53. And the probability of a male given that the person prefers math. All right, so we're only looking at our math people, 8 out of 18. And when you do that, it works out to be 44% or 0.44. So these are not the same. So the question is, what does that mean? Are they independent or are they not? And hopefully you realize they're not independent. They would need to be the same. The probability of being a male, given that you prefer math, is not quite as high as just probability of randomly choosing a male. Okay, so the events are not independent. Students who prefer math are less likely to be male than a randomly student in the entire 6th grade class, which we saw was about 53% of them. Okay, well, how about gender and social studies? Are those independent? Okay, so let's make sure we can see all our subjects here. So we're going to do gender. Let's do female this time. So we'll say probability of being a female. Find that out, please. And then find out also the probability of being female given that person prefers social studies. Play the recording when you have those two. Okay, so hopefully all our females are 27 out of 57. And then probability of being female, given that someone prefers social studies. So we're just looking in this loop right here. So 9 out of 19. And it turns out when you work out the decimals or simplify each of those, they're exactly the same. So 47% in each case. So that just means they are independent. So we said the rationale is students are just as likely, they have a 47% chance of being female, whether they prefer social studies, which is this, or just the population in general. Okay, so finally we just want to formalize this a little bit. The general multiplication rule, well, our formula for conditional probability is probability of B, given that A already occurred, we said is the probability of A and B both occurring divided by the probability that A already occurred. All right, so doing a little math to get this numerator by itself, we would multiply both sides by probability of A, right? So these would divide, come over and multiply the probability of A on this side. So the probability of A and B, this is our general multiplication rule, meaning doesn't matter whether they're independent or not, is the probability of A times the probability of B. That was our rule from before, right? Just multiply with an and, given that A already occurred. And if they're independent events, well, there's not going to be a difference here, right? Probability of B, given that A is going to be the same as probability of just B. Thanks for watching.